Welcome to this semi-plenary lecture on modeling and control of pharmacodynamics. My name is John Bautherp Jørgensen, and I'm from the Technical University of Denmark. I will chair this session. It's my pleasure to introduce you to Carolyn L. Beck. Carolyn is currently an associate professor in the Department of Industrial and Enterprise Systems Engineering at the University of Illinois at Urbana-Champaign. Her research activities are focused on the development of model reduction methods, mathematical systems theory, clustering and aggregation methods, and she applies these methods to biomedical engineering and networks. She has also been a visiting faculty at KTH in Stockholm, Stanford University in California, Lund University, Sweden. While on faculty, she has received national research awards, including the Career Award from the National Science Foundation, the Young Investigator Award from the Office of Naval Research. Carolyn received her PhD from Caltech, her MS from Carnegie Mellon, and her BS from California State Polytechnic University, all in electrical engineering. Between her MS and PhD, she gained industry experience by working as a research engineer at Hewlett-Packard in Silicon Valley. Without further ado, it's my pleasure to give the word to you, Carolyn.
Okay. Thank you, John, for the introduction, and thank you to the organizers for inviting me. So as John said, today I'll be talking about modeling and control of pharmacodynamics, and mostly in this talk I'll be focusing on one specific problem, that is the anesthesia control problem. But what I'll do is I'll start by discussing a couple examples of pharmacodynamic control problems. This is work that I've done with collaborators over the past 15 years or so. In terms of the anesthesiology, this has been done in collaboration with Mark Bloom, who's a PhD MD. He's an anesthesiologist at New York University, and then grad students Yevgeny, Matt, and Hui Hung. And the work that I'll be discussing today is obviously application focused. So I'm going to start, as I said, with a couple examples, namely just a quick overview of what the anesthesia control problem is and a quick overview of what the blood glucose control problem is, because there are some similarities, although I won't talk about control methods for that problem. And then what I'll do is I'll discuss the sort of classic approach to modeling that has been used in numerous control designs for these problems, in particular for the anesthesia control problem, and that is compartment models. And what I'll try to do there is highlight sort of the main issue that we run into in using compartment models for control, and that is that they're inherently single input, single output, and a lot of these problems that we look at are not. And then I'll talk about our work. I'll focus on the anesthesia control problem, the models, the multi-input, multi-output model, structures we've developed, and look at some of the control designs, linear parameter varying control, and L1 adaptive control, and some of those results. Okay. So as I've said, the main problem that I've looked at is the anesthesia control problem. I don't know how well you can see this, but this picture on the bottom right here captures the reality of anesthesia control today, and that is you have an anesthesiologist who's near the patient, observing the patient, and also simultaneously observing a large bank of instruments. So that's what the anesthesiologist does, and what we do as control engineers is we like to think of the problem like this, but I can assure you the anesthesiologist does not. So we tend to think of these block diagrams, and this top row represents really the instrumentation, which may be fairly accurate then. They're engineered systems. The bottom row of blocks here represents a patient. It's really not that clear that we have such a simple sort of delineation of subsystems in the patient. So what does the anesthesiologist do exactly during surgery? Well, we all know the anesthesiologist is responsible for administering all of our anesthetic agents. These include sedatives, which is the drug, the control we focus on, but as well analgesics, that is the painkillers, and neuromuscular blockades. As well, the anesthesiologist is responsible for maintaining all the ventilation parameters, so they have to make sure that you get the proper oxygen-air mixture throughout surgery, and they have to make sure that all your vital signs stay within safe or healthy ranges. So that is your blood pressure, your heart rate. They watch your EEG, and they're also responsible for monitoring your blood chemistry. So it's pretty clear, and we're all aware of the fact that the anesthesiologist is basically not only the multi-input, multi-output controller in the process, but as well serves as a sensor and an actuator for a lot of these processes throughout surgery. So in our work, which I'll discuss in more detail shortly, what we've tried to do is look at partially automating this process, not only so that we can tailor the dosing of the anesthetics to the patient, but also so that we can essentially reduce the workload on the anesthesiologist, so the anesthesiologist can focus on safety critical tasks. Okay, so to implement feedback control, what we need to be able to actually sense, hopefully quantitatively, a lot of these signals. So we need some means of sensing the levels of sedation, the effects of the analgesics, the painkillers, and the effects, the adequacy of the neuromuscular blockade that's been given to the patient. And as well, we need mathematical models of the patients. And in fact, we don't really have any of these things for the anesthesia control problem. There have been some developments, which I'll discuss, towards sensing signals for some of these. But for the most part, there's no widely agreed upon sensing levels for most of these signals that we need. As well, in not only the short run, but the long run, if we implement feedback control in anesthesia, we really need to take account of the fact that there's going to be an anesthesiologist in the loop, so we're going to have to look towards designs that acknowledge the human in the loop. And through surgery, it's not purely a feedback mechanism that the anesthesiologist is performing. There's actually feed-forward information that comes from, for example, the surgeon to the anesthesiologist. The surgeon will say, I'm going to start the incision. This patient will get an increased dose of anesthesia before that incision is made. So we can't, in the long run, look at this as purely a feedback control problem. Okay, so in the diabetes control problem, I think this is basic physiology. Probably everyone knows this, but we'll go through it pretty quickly. What we have is a system that's essentially regulated by your own body, right? Your pancreas or your control center, essentially. And in diabetes, this is either not working correctly or your body isn't responding correctly to the signals from the pancreas. So what happens is within your body, when your blood sugar goes up, your pancreas secrete insulin. And that insulin tells other cells in your body, your fat cells, your muscle cells, some of your red blood cells, that they need to increase their absorption of blood glucose, the sugar from your bloodstream, and that returns your blood sugar levels to normal, right? On the other hand, if your blood glucose is low, your blood sugar is low, then the pancreas secrete something called glucagon. And that hormone, these are both pancreatic hormones, tells your liver to release more glucose or more sugar into your bloodstream to return your blood glucose levels to normal in your bloodstream. And this also tells your liver to actually start producing glucose from storages. And so your body wants to maintain this blood glucose in it's not a terribly narrow range, but within some range, typically something like 70 milligrams per deciliter to about 110 milligrams per deciliter. If your body drops below 70 milligrams per deciliter of blood glucose concentration, that's called hypoglycemia. That's a problem for anyone, not only the diabetes patient. It's when you get lightheaded, etc. Your blood sugar can often go above 110 following meals. For example, it can be up to like 180. That is when your pancreas goes into action and releases insulin. So the feedback control problem for blood sugar, as we have it implemented today, is usually enacted in this manner. The patient serves as their own feedback controller, right? So they take measures of their blood glucose levels, and then in response to that, they administer insulin to themselves, right? And it used to be commonly that to do this, they'd prick their finger, they'd put a sample of blood on a test strip, put it into a home metering device, wait about 15 seconds, and then get a blood glucose reading and give themselves an injection of insulin. Increasingly, this has been replaced by what are called continuous glucose monitors. It's a sensor the patient wears that's actually sampling interstitial fluid, so it's not directly measuring blood glucose, it's estimating that from interstitial fluids. And then as well, we have these subcutaneous continuous infusion pumps that the patients can also wear, but they still actually serve as the activator for the insulin pump and essentially serve as the feedback control mechanism. So to do automated feedback control, for this problem, we of course need the same thing. We need sensors, which we have. We have these glucose monitors now, and we have the insulin pumps, so we have those. But we also, again, need mathematical models for the patients, and there are models that exist actually for both the anesthesia and the diabetes control problem. There are these compartment models I'll talk about. As well, in the long run, we might want to think about moving towards a multi-input, multi-output, or multi-input anyway, control mechanism for diabetes. It would be, it would actually do a much better job. This is what a lot of research projects are looking at. So some people have considered including glucagon as an additional input to capture the effect of low blood sugar. Currently, when your blood sugar is low, as a patient, you eat something to try to get your blood sugar back up. And what people have looked at so far is including this as one of the inputs in these continuous infusion pumps. But more immediately, what researchers are looking at is means to include information about meals and activity levels of the patients into the control mechanism. So how to do that would require the patient to actually provide feed-forward information about their meals. Activity levels, people have actually considered using accelerometers to essentially measure the activity level of the patient and use that information in the feedback devices themselves. At this point, there's been a lot of work on devices, and I think it's in the news a lot, and there's a lot of work in this community. I think currently the only automated feedback device that's being tested right now is for use on children during the evening, right? So they won't take meals or be excessively active. Again, so we could look at this as a multi-input, multi-output problem, and we clearly have a human in the loop, the patient's in the loop, and we clearly have some feed-forward information that's being used. And here's actually a picture of one of the sensor pump devices. They're fairly common now that are out in the market. They first appeared in '96, and so it was, I think, Medtronic that had the first device. There are a handful of them available now for diabetes patients. Okay, so neither of these problems are new to control. There's been a lot of work in the control community on them, and actually in the medical community. The anesthetics control problem has been, this is the earliest reference I could find to work on the anesthesia control problem. So it's over 60 years, 64 years ago. People were looking at automated feedback control of sedation, in fact. That's a EEG signal. And it continues to be obviously looked at today. I put in one of the most recent publications where there is a implementation and testing of a PID controller for propofol control. So that's, again, a sedative. And I've only listed two There are hundreds and hundreds of references you can find on controllers for sedation. In fact, the large majority of them are CISO, looking at a single sedative anesthetic agent in to the sedation level out via various signals. Diabetes as well. The control and medical industry have looked at automating dosing of insulin for over 50 years. I think it's been getting more press recently. There's something called an artificial pancreas project. That's actually what they call the device they're designing. It's an external device, not an internal device, to automate or partially automate insulin and glucagon probably delivery to the diabetic patient. Again, there's hundreds of articles. Just in the last 5 years, you can find over 40 different feedback designs that have been implemented in a test scenario in the literature. As well, there's been other areas that have received a reasonable amount of attention from the control community: chemotherapy, HIV, and even additional endocrine type problems. So, as I said, most of these control efforts have focused on single input, single output control problems. So like a subset of the actual control problem that exists. And most of them, or most of those, have used these compartment models, something called a compartment model, as a model for basing their feedback design on. So I just want to spend a little time giving a quick overview of compartment models, and I assume, again, that a number of people may be familiar with these, so we'll just give a quick overview of what these are. So basically, compartment models take the perspective that we can view our body as a series of compartments, or essentially like stirred tanks, that the drug flows through basically from input into a central compartment through peripheral compartments, and in this partition of the compartment model, what we're looking at is how the body essentially processes the input drug. In this case, I put anesthesia. So you have an input drug, and what the output of this partition is essentially the concentration of the drug in the blood, and that's what we call the pharmacokinetic model. And then cascaded with that is typically what we call an effect compartment, where we look at the essentially dose-effect relationship. So from blood concentration to particular effects. So this is a particular output signal from the patient: heart rate, blood pressure, EEG. Okay, so these models typically look at a single drug input to a single effect, or say vital sign output, and a little more specifically, the pharmacokinetic models are typically essentially linear time invariant type models. They're ordinary differential equations, basically. So what's shown here is a classic representation where we have our input drug, and then we assume that the states, so we can view this as a state space model, the states are the concentrations of drug in the associated compartments, and these parameters, these Kij, are essentially the clearance and distribution rate constants. So if we take this perspective for our model, then, as I said, our states are concentrations, and we have to impose this constraint that the states are always non-negative. So this is essentially a model that is, it's a positive system, and typically we find these parameters using a gray box ID type method. So this is these are empirically derived. They're based on essentially trying to view the body, as I said, as a series of compartments where we're looking to describe the sort of mass balances of the drug in the system. Here, the central compartment is the main space where the drug is input. So if we're talking about, for example, Inhalational anesthetics, that would be the lung volume. If we're talking about intravenous drugs, that would be the intravascular volume, so the blood volume, intravascular blood volume. And then these peripheral compartments essentially are meant to represent groupings of, say, organs and tissues in essentially descending blood flow order. So the first compartment might be, say, the liver, the kidney, and the spleen. And then as you go down the series of these compartments, the last compartment would be like bones and fat. Okay, so it essentially is grouping the tissues in your body into these compartments and trying to describe diffusion and clearance throughout to arrive at some essentially steady state drug concentration. The pharmacodynamic models are typically nonlinear, static nonlinearities. And as I said, they're really trying to capture the dose, the drug concentration to effect relationship. And this is a classic form. They're typically sigmoidal. You may recognize this as being essentially the Hill equation. And there's some, originally, some argument made for using these Hill equation models from a physiological perspective. But in fact, there's a fairly weak connection between the Hill equation and the physicochemical reaction that occurs in pharmacokinetic, pharmacodynamic processes. The Hill equation is really useful for physicochemical equilibrium reactions, which is not actually what a PK/PD process is. So these are all also empirically derived. Usually you get some data from a patient and they're very individualized. They're basically fit to an individual patient. So you need some measurements of sort of concentration to effect for the patient. And here, this is the initial effect, and this is the maximum effect. And then you basically determine what this parameter gamma is and curve fit the data. And so that's how you derive the pharmacodynamic models. So as you can see, these are, I call them basically gray box models. They have some loose physiological association, but I think it's fairly loose. They're nonlinear. They're single input to single output. And so they are useful for CISO control design. But if, in fact, we truly have a multi-input, multi-output control problem that we want to look at, then we need some other modeling construct. And I think that because so much of the work, in particular in anesthesia, has focused on using these compartment models, I think to some extent it has actually held us back from implementing these controllers in actual surgical settings. And so it was my sort of perspective that we really needed to try to explore MIMO, or multi-input, multi-output, model structures and model control methods for some of these problems and see if that would take us a little bit farther. So focusing on the anesthesia control problem, I'll tell you a little bit now about some of the models that we constructed, the MIMO models, and the control designs and we found. Okay, so just picking up where we left off, as you recall, what we said is we need some means of sensing sedation levels, pain relief effect, neuromuscular blockades, and we need mathematical models of the systems. In terms of sensing, of course, the signals we'd like to be able to sense, the three components of anesthesia. Actually, we have means of sensing neuromuscular blockade effects. We usually use surface electrodes or piezoelectric type devices attached to some part of the patient's body, typically somewhere in their hand. And in response to electrical stimuli, we can determine whether the neuromuscular blockades have taken adequate effect. As it turns out, we focused on controlled sedation, and as it turns out, the neuromuscular blockade agents effects are typically uncoupled from the effects of sedatives, so it's considered a somewhat separate control problem, so we haven't actually considered this in our work ourselves. Analgesics, however, and sedatives are synergistic, so if the patient's administered analgesics, it usually enhances the effects of the sedatives. And sedatives, usually, actually, most sedatives provide some analgesic effect. There's absolutely no means of, at this point, of measuring quantitatively pain relief in patients. This is one of the things that anesthesiologists observe when they're in surgery with the patient. They're actually looking for physical responses to surgical stimuli to determine if the patient has adequate pain relief. There have been some proposed methods over the years, but nothing that's been accepted. Sedatives or sedation effects, on the other hand, there's been a lot of commercial development and industrial research over the past about 15, 20 years looking at devices and signals that provide some quantitative measure of the level of sedation. GE has developed some instruments. They use what they call spectral entropies. Cleveland Medical Instruments has developed some instruments. They use what they call wavelet analysis methods. And Covidien, or originally Aspect, about 15 or 20 years ago, proposed something called the bispectral index. And this is what we focus on using in our studies, is this bispectral index, or we just call it BIS. So there's been thousands of studies done with BIS that show that it's a fairly effective measure of sedation level. It's derived from the EEG. Typically there are 4 or more EEG signals that are processed. So you're looking for a certain synchronicity in some of these EEG signals that tell us something about the level of unconsciousness. And so in our work, what we use is data from a clinical trial data to start, where we have inhalational sedatives and BIS outputs as a measure of sedation level. And we also have a number of other vital signs, and we have some blood chemistry data. We have mostly reduced this to looking at the BIS output, the blood mean arterial pressure, heart rate, and then our input is this inhalational anesthetic. It's called Isoflurane. And as well, this data contains responses to a number of stimuli. So this is actually, as I said, a clinical trial. So these weren't patients. I call them patients. They're volunteers. So throughout the trial, each one lasted somewhere from 3 to 5 hours for an individual. They did what are called Evoke potentials tests. So that is, they applied electrical shocks to the wrist of the volunteer. There's also sort of a typical surgical stimuli, that is this laryngeal mask insertion and removal, and that the volunteers were all intubated essentially for safety reasons. And then throughout the trial, the clinicians conducting the trials would essentially harass the patients. They would shake them and yell at them and squeeze their trapezius, etc., and then make some sort of evaluation of their alertness level following that through the course of the anesthesia. I guess one more thing I want to say is this BIS signal is unitless, dimensionless. It's normalized to give a reading between 0 and 100. 100 means you're completely alert. Hopefully that's where we all are right now in this room. When we're in surgery, it's preferred that we're somewhere between 40 and 60, depending on what's being done. So 60 would be, say, your sort of light sedation for things like wisdom, tooth removal, etc. So our control goal here was we wanted to track a BIS reference trajectory signal while maintaining our blood pressure in a healthy range. And originally we were looking at maintaining heart rate as well. But what we discovered in the process of analyzing the data was that the heart rate there's no effect on heart rate from isoflurane. So that was one of the things that we found in the process of looking at the data that we got from the trial. And we really like these to be both adaptive and robust to patient variability. So here's an example of some of our data. You can see that in the back. I'm not sure, it's a little bit light. So these are our inputs. So this is the anesthetic input. So it's as a percentage volume concentration in the air mixture. So I don't know if you can read that. It's not very high. So we say up to maybe 1.5–2% volume of our air mixture would be this inhalational anesthetic isoflurane. And we're trying to sort of implement some basically step functions in this trial. And here is actually a sort of quantitative rendering of the stimuli that were applied to the patients throughout the trial. So we actually developed these quantitative models. We had basically qualitative notes of what was being done to the patient. So obviously in consultation with the anesthesiologist, we came up with a series of quantitative models of the input disturbances or stimuli. And these are the outputs that we started with. This is the BIS signal, so this indicates the level of consciousness. So this is early on, before sedatives have taken effect. They're fairly alert. And then at some point, we want to sedate the patient. If you've ever been sedated, you know it happens pretty quickly, right? They say things like count backwards from 10 and you get to 7 or something, I don't know. So here's going into induction into sedation, and these are the different levels of sedation, and then we come out of sedation again. This shows the heart rate, which, as you can see, doesn't exhibit much trend. And this is the blood pressure, the mean arterial pressure, which is typically decreased throughout the course of anesthesia. And you can see there's some disturbance effect here that occurs in most of these trials, which I can talk about later. Okay, so what we'll look at first is, as I said, we'll sort of take a chronological look at the work we've done, is some piecewise linear and linear parameter variant models, that multi-input, multi-output models that we developed from the data in order to try to do some MIMO control design. Okay, so what we did is we had our clinical data, and we basically identified a pair of state space models for each patient. These are black box. We use subspace ID methods. So we have, say, essentially like 2 inputs and 2 or 3 outputs. So we developed linear models representing the awake state and linear models representing the sedated state. We originally thought we'd have to do 3 or 4 models for different levels of sedation, but basically we found out we only really needed awake and sedated. And so we found fairly low order models, 3rd to 5th order, for each patient in each state, sedated or awake. And so we have these essentially discrete time models because this is sample data. And then we initially looked at switching between alert to sedated based on a specific BIS value, a sedation level. And we implemented the switching so that our output remained continuous. So we do sometimes have a jump in the state, but it doesn't matter. It's black box state. We're doing output feedback control anyway. So this just shows how we partitioned the data we have into alert and sedated states. We use this BIS level of 70. So there's a large body of clinical trial data on BIS and level of sedation, and it's fairly widely accepted. There's some studies published that at 70, as we're either transitioning down or coming up out of sedation, that's the point at which we're transitioning into a sedated state or an unconscious state and coming out of a sedated state. So I think what was found was that it's basically the median at which half the patients are effectively sedated, although lightly, and half are not. And so as you continue past that point, you're considered sedated. So that's how we partition the data to do our subspace ID for the 2 state space models. Then from the piecewise linear models, because we wanted to do LPV control design, it gave us some robustness guarantees. There weren't very good methods for doing switching feedback design with guarantees at the time, so this was done between, say, 2000 and 2006 in my group. So we converted essentially our piecewise linear models to linear parameter varying models. So basically what we're doing here is essentially smoothly gain scheduling between our awake and sedated models with respect to a BIS value. So we modeled this essentially switching or smooth transition using this time varying parameter delta, which essentially captures, what this is doing is essentially capturing this sigmoidal type dose effect relationship, right, for this MIMO model, okay, that we see when we administer drugs and go from, in this case, alert to sedated. And then we essentially developed a linear parameter varying model that smoothly transitioned from alert to sedated. So basically when delta is -1, we're fully alert, and when it's +1, we're fully sedated. This just smoothly transitions based on the BIS value itself. Okay, so this gave us these linear parameter varying models. These are, to be rigorously correct, quasi-LPV, because we're actually relying on a measured output. Okay. And then what we wanted to do was put this into our essentially LFT form to do control design using the toolboxes available to us at this time. So in fact, we took this nice, smooth, linear parameter varying model over this parameter delta, and essentially this involves another approximation to be able to put it into this LFT form. It's basically a Stone-Weierstrass type approximation to this function. Okay, so that we get it in this block diagram form where it looks like a standard linear time invariant system, except that now it is evolving not only with respect to our time shift operator, so I use lambda to represent the time shift operator, but also with respect to this parameter delta, okay, that helps us transition from smooth to alert. And here's some results from these models. So this shows some simulation results using the LPV model. Then the black line, you can see the black line kind of faintly there, is the actual patient data. Okay, and the red line shows the response the model gives us for the LPV model. And because these were a high order, I've also model reduced these. So this shows the results of the model reduced LPV models. And then we also designed compartment models to compare. Because the compartment models are the standard, you pretty much always have to compare anything you do in this field to compartment models to show that you're either the same or better. So the blue, if you can see it, the sort of a little bit smoother line shows the compartment model response. Okay, so this is anesthesia and disturbance. Well, it's just anesthesia in to BIS out. And then this shows the heart rate models, and this shows the blood pressure models. For the LPV models, when we're doing the subspace ID, we broke the data into two parts. So we have an estimation part that we use to actually construct the models, and then, of course, our validation part. For the compartment models, you have to use all the data. So the compartment models are constructed using some nonlinear regression methods that require you to use the entire cycle of data. You need to actually have some sort of hysteresis type loop present in your data, which requires you to go from alert to sedated to alert again. Okay, so the compartment models were constructed using all the data, but the LPV models were constructed using the first half of the data and then verified on the second half. Here's a second example where what we did was we wanted to see how well one model worked for a model for one patient worked for another patient's data. So we took the model we constructed for our third patient, or volunteer really, and applied the data for patient 1 and then compared it to the output data for patient 1. So again, the black shows the actual patient 1 data, and the red shows the response of the LPV models. So the LPV models are multi-input, multi-output. Okay, so this is all one MIMA model. And then the blue shows the response of the compartment models. So using patient 3 model with patient 1 data and seeing how well it captures patient 1 response, basically. Okay, for adaptive control, we had a slight change at this point. This is a later design. I'll talk about this a little bit more when we get to the actual control simulations. But all we need here are linear models based on the theory for adaptive control design, and at this point where we were with respect to what the medical people were telling us about what they wanted to implement. Okay, so in adaptive control, the standard structure is that we need to find this LTI system transfer function. It's assumed that it's going to be strictly proper, so we need a strictly proper transfer function representing the response from the inputs and the disturbances to the output. Okay, so in this case, our output is BIS, and of course, in the MIMO case, BIS and MAP. The inputs are anesthesia flow, and then we have these disturbances. We assume they're time varying. They can actually be a function of the input in the adaptive control, L1 adaptive control construct. The only assumption is that this disturbance, so this would be like our surgical stimuli possibly, or it could be that we just want to leave that as being disturbances that occur naturally during surgery, like blood loss. But this disturbance is assumed to be Lipschitz, and we're assuming it has some Lipschitz constant L. And so what we did was we used state-space identification methods again to construct a standard linear model. Now, you know, I've listed this as being A sub S, B sub S, C sub S, which is the same notation I use for the sedated model in my LPV modeling construct. And that is because basically when, as we proceeded through the process of modeling and control for anesthesia, we got to a point where our medical collaborator said, look, there's no way, they're not going to let us implement feedback controllers where we take the patient, where we induce sedation, run the course of anesthesia, and then bring them back out of sedation, essentially for the whole trial or surgery. They're not going to approve that. We need to have the anesthesiologist bring the patient into the sedated state and then run the controller, and then have the anesthesiologist bring the patient out of the sedated state. So what we were focusing on at this point was just looking at feedback control design that would be enabled once the patient was already sedated. So we only needed the sedated model. So that's why we call it A sub S, B sub S, C sub S. And this shows just a quick example of some of the estimation and prediction results for this model. And of course, it looks similar to our previous results because it's basically just the linear model for the sedated state. Okay, so what I'll do now is quickly go through the controller synthesis. I'm not going to spend time talking about how you do linear parameter varying controller synthesis. If you have questions, I guess we can talk about it at the end, or I can talk about it in detail later. I'm just going to sort of quickly run through, refresh everyone's memory for those of you who are familiar with this, the process. So we assume that we're starting with this linear parameter varying system. So we have this G of delta and lambda. So this is our time shift operator and our time varying parameter. We have it in this linear fractional form, right? So it looks like this sort of extended or multi-dimensional time invariant system. And what we want to do then is take this model and compute some controller, I've shown as a discrete time controller, preferably a linear controller that meets our stability, tracking, and disturbance rejection performance criteria. So normally such a linear controller would have the standard state space formulation, but because we're starting with this parameter dependent model, in order to meet all of our performance criteria, we're going to have to actually design a controller K that's also linear parameter varying, basically, okay? So using the LFT formulation, basically we have, this is our plant, and what we want to do is find a controller that essentially also evolves with respect to our time shift operator and our parameter delta, right? That meets our performance criteria, and there are in fact software algorithms to help us do this, and they essentially rely on solving this set of coupled LMIs. And as I said, I'm not going to go through the details, but our plant data is in the A's, B's, and C's in these matrices, and what we're looking for are solutions to these LMIs, the RS, X, and Y matrices. And that will give us a controller K of delta and lambda. So as I said, there are toolboxes, Matlab toolboxes that can do this design for you, given your performance criteria and your system models. They're explicit formula. They're even messier or uglier than these LMIs, so I didn't list them here, that tell you what your controller will be. It's basically based on your plant data and these solutions. So what we'll do is look at some of the control design results we got from the LPV controllers, and then we'll talk about the adaptive control. Okay, so here I have an example of one simulation response. This is patient 1 again. What we've done is we've constructed this reference BIS signal. We want the patient's BIS output to follow. And then we're also trying to maintain our map within a pre-specified safe range, 60 to 110 milligrams of mercury. And we're also looking at, how much control effort or anesthesia is actually required to attain essentially the tracking and maintaining the map within a pre-specified range. So this is a patient 1 control design with patient 1 model, basically. And as you can see, we did a pretty good job of tracking the BIS signal early on, but when we got near the switching threshold, so this is actually one of the hardest cases, is we tried to look at what happens when we're near that switching threshold. You can see that we had a lot of difficulty here maintaining a smooth BIS trajectory, right? So this obviously needs more work. And as I said, this was sort of one of the hardest test cases, is we ran this a little bit below and a little bit above this switching threshold to see how the controller performed. So this actually needs a little more work. We also looked at how controllers perform on other models, essentially. So here's an example, just the same one, just to see the difference. Again, this is what we had on the last slide. If we take the same model, patient 1 model, and we implement the patient 3 controller, you can see again it did a reasonable job of tracking the BIS early on, but around that swishing threshold we had some difficulties, although I think actually this looks a little better than the original controller for patient 1. And again, we can see that the input anesthesia is almost the same. There are some differences. It's a little more anesthesia there, etc., but they're almost the same. And this is just the BIS, as I said, the BIS reference tracking here that we looked at, the sort of how what we were thinking about was, would it be possible to come up with somewhat nominal models and controllers to start the process, and then as time went on, sort of use some adaptation or recursive ID to update models and controllers throughout the process, but having an initial sort of nominal or central controller at the start of a process. That was what our idea was originally. So we wanted to see how robust our control designs and models were. Okay, so let's look at the L1 adaptive methods. Again, I'm just going to give a quick overview. I think we have an expert in the room if there are any questions about details. But just with respect to time, let's sort of quickly look at what are the main ideas, and feel free to correct me if I say something that you think is not quite accurate, Naira. All right, so what are the L1 adaptive control methods looking to do? Again, they're looking, in our case, but in general, to track a reference input under modeling uncertainties. And the claims are that these controllers guarantee asymptotic tracking with uniformly bounded system inputs and outputs, and that they prevent high-frequency oscillations in the control channel. And there's some theoretical work in the papers that describe the theory for adaptive control that sort of have the proofs, I guess, for these things. So sort of a quick overview of what are the steps that you go through when you're designing an L1 adaptive control. So as a user, what do you do? Well, first, what you do is you say, well, we want to track some reference input R, and we want to track that reference input. We want our output to track the reference input, so this would be our BIS in the anesthesia problem, according to some desired model M. So we have some desired model. We know what it is. We want our output to take a certain profile according to this model M. So we say, okay, let's suppose then that we can look at our original input-output relationship for our system. And as you recall, this was the system model that we're using for the adaptive control design. So just the basic LTI model where we assume we have an input and disturbance. Okay, so let's assume that instead of writing our relationship like this, we use this desired reference model M. Whoops. Okay, then we can rewrite the input-output relationship in this form where basically this captures the same relationship, but now we're using this parameter sigma. This is going to be our adaptation parameter. And this is essentially capturing all the differences and uncertainties in our model. Okay. And as an example, throughout this discussion, I'm going to assume that we have a SISO problem, just to make it a little more straightforward, and that we have this simple first-order model for our system, just a first-order low-pass system. Okay, then what we do is we say, okay, so now we have this model we assume that we want our system to follow. What we want to do then is think of what our ideal closed-loop system would look like. So we have what we call this closed-loop reference system. So this is our ideal closed-loop system. So we're saying, now let's suppose we go and we close the loop with this control, feedback control law. And then what we're going to do in this case is design this filter, C of S, so that we attain some ideal closed loop performance. Okay, so this is essentially saying this is what we want our system to behave like. Okay, and essentially our tuning valve is this filter C of S. So we're going to design this filter C of S so that we attain this ideal closed loop behavior. Okay, so that's the next thing we design. So far we're choosing a model M of S, and we're going to design this filter C of S so that we have basically the behavior we want. And then what we do is our adaptive controller basically tries to track this system. Okay, so we have an M of S and C of S that we design, and they have some constraints. Basically, we have to design C of S and M of S so that we satisfy this essentially small gain stability criteria. And this is essentially a small gain stability criteria with respect to the transfer function for the disturbance. Okay, so our disturbance input, as you see, we have this Lipschitz constant. We've assumed our input disturbance satisfies this Lipschitz condition. There's our Lipschitz bound. Okay, so basically what we're doing here is saying we're going to pick a M of S we want our system to behave like, and control and close a loop to behave ideally using the C of S, and they have to satisfy these constraints. And if we do that, then we have guaranteed bounded input, bounded output stability of our ideal closed loop reference system. And then we design our L1 adaptive controller, as I said, basically to track that ideal system. So we call it an output predictor. It's basically, this is what we're using to try to follow the ideal output. The equations I've written here are assuming that we have that simple first order plant model M of S, desired plant model M of S. That's why we have this little parameter M here. So this is basically just giving us this y of s equals m of s plus times y plus sigma relationship. So that's our predictor. Then we have this, what we call parameter adaptation law. So this is where we're trying to use this parameter to inform how our system how to adapt so that we can track the ideal closed loop system. So this is probably the heart of the adaptive control design here. This involves a projection type operator that essentially constrains this uncertainty or adaptive parameter to be bounded. Okay, so it's essentially projecting it to stay within a compact space. Okay, so that's what that does. And then we have this adaptation rate, right, determines how quickly we adapt. And we have this gain parameter P, which is actually coming from a Lyapunov equation. Okay, so this is all shown for SISO. For a SISO system, this is fairly arbitrary, but for MIMO problems, we're actually solving a Lyapunov equation to find this P. And then using these elements, our feedback control law, it looks similar to the one for the ideal closed loop reference system, right? We have our filter C, and now we're using this estimated parameter essentially. And then we implement this, and then it can be shown, in fact, that this feedback controller essentially tracks the ideal system, and our output error is guaranteed to be uniformly bounded. So note the design parameters from the L1 adaptive control determine the error bound, as well as this constant K, which is actually proportional to L, the Lipschitz constant for the disturbance. Okay. Okay, so some simulation results for the L1 adaptive design. Okay, so as I said, I'm just going to remind you. So these were more recent designs. Probably started doing these about 2007. The initial designs were done with a master's student, and those are the ones I'll show, some of those results. This is really looking at controlling the BIS only during the sedated state. Remember I said we changed basically some of our performance requirements or implementation requirements. So here the red signal is our reference BIS trajectory we're trying to track. Okay, I need to go faster. And then this black line shows the system response. And here we see the isoflurane input that was used to attain this reference trajectory. So you can see this is fairly smooth. In particular, if you look around 70, we have a lot less, essentially, chatter oscillation in our control signal. And this gives us, tells you what design parameters were used. So it's a very simple first-order system, first-order filter. This is just another example. This is patient 5. Same thing. The red line is the reference trajectory, and the black line is the BIS signal. And this shows our isoflurane usage. And the control design was almost the same. There's a slight difference in our filter. And here we are looking at robustness of these controllers. So what we did is we took the patient 1 controller and we used it on all our other models. This shows 3 of them, patients 1, 5, and 6. So the reference trajectory we're trying to track, again, is this red dashed line. And the responses, patient 1 is the blue line, which is, this is a patient 1 controller and the patient 1 model response. The patient 5 response is black and the patient 6 response is green. And you can see that all of them perform pretty well and follow the desired BIS reference trajectory fairly smoothly. The isoflurane is a little more interesting. The patient 1 and 5 isoflurane input is pretty similar, but you can see that patient 6 required more isoflurane to attain the same performance in the simulation. So just looking at if we use patient 1, the patient 1 controller and all the other models, some additional performance analysis. We looked at the tracking error and the isoflurane usage. One of the goals we said we wanted to attain originally was to optimize the dosing. So we looked at the simulated consumption of isoflurane and compared that to our other controllers. We compared it to the LPV controllers over the same time range and to our original, basically the isoflurane consumed when the anesthesiologist was a controller. And then we also looked at actual MIMO designs. So this is just the results. They're fairly similar, but you can see now we have disturbance really affecting the system, so you can see a little bit more oscillation here. And then this shows as well our map output. So we went to the two outputs. And this is maintained within the desired range. And this is where we are currently. So these were, as I said, the first pass at designs. So now we want to include some of our implementation issues. We want to look at some sampling effects, possibly consider multiple filters in the design, and anesthesiologist enable-disable control. So here's a switch for anesthesiologist enable-disable control. We have some sampling effects we're taking into account. We have 2 filter modes we're allowing, and we have actually a limit on how much anesthesia we can give the patient. So we have basically an input saturation control. So that's where we are now. We're looking at, as I said, implementation issues and how it goes into our control designs, and of course looking at more complicated MIMO designs for the system. So we're trying to incorporate some enable-disable control, which leads us to looking at sort of situational awareness type issues. As I said, we have input bounds for our drugs. We want to incorporate multiple synergistic anesthetic agents into our models and into our processes. But to start, we'll just look at one anesthetic agent. And I just want to note, I say 60 years and counting. We've been looking at this problem in this community as well, the medical community, for 65 years. We haven't implemented devices. There are no approved feedback devices out there yet. But I do want to note that recently, this is not a closed loop, but it is an approved anesthesia administration assist device that's on the market that provides delivery of a sedative called propofol for minimal to moderate sedation. This is during gastroenterology procedures, so it's non-surgical. But I think it's really positive that this has been approved and is now a device on the market, because for the longest time, it took years and years to try to get the FDA in the US to approve even target-controlled infusion, which is essentially what this is. So we are making some progress, and hopefully we'll make more in the future, near future. Okay.
Let's thank Caroline for an excellent talk. So I think